First lecture this morning is by Tom Bridgeland on Twistor spaces and Donaldson-Thomas invariants.
Okay, thank you. Thanks, Nigel, and thanks to the organisers for giving me the chance to come here and learn about twistor theory. I'm also reminded of my time I was an undergraduate in Cambridge. I would spend a lot of well, there was one term where I spent my time hiding from Nigel because he was my Part 3 essay supervisor, and I didn't want him to realise how confused I was about everything. I guess I ran out of hiding places now. So, in some sense, this talk is about this equation. I mean, if you're an equations person, then this is maybe... So this is some version of Plavansky's second heavenly equation. I guess, so this is from 1975, so nearly 50 years old, and he would have considered the case n equals 2. And then this would have just been 1 or minus 1. There's not much. This is a skew thing you put in here. But anyway, so this is some kind of obvious higher dimensional generalizations of that. And he wrote this equation down in connection with solutions to Einstein's equations. So this story is really, the story I'm telling is basically I was thinking about something completely different, namely Donaldson-Thomas invariants, and I ended up with this equation, and I wrote it in my paper, and then Ian Strawn read my paper and said, hang on, that's Plavansky's equation, and then we got this, obviously then you get a link to hyperkähler geometry and so on, which has been very interesting for me. So there were various things I could have talked about. I mean, one of the things I'm more excited about is using these ideas, we have some kind of interesting solutions to this equation, which are even algebraic in some way. But I was kind of prevailed upon to give the bigger picture of where this equation comes from in DT theory. So I'm going to try and explain that, and that's the story that I've been talking about for quite a while. So apologies for those people who have heard it before. Okay, so there's only going to be one page of introduction. So let's see, if I press this red button, what happens? Good. So this is a story about some things called enumerative invariants, which show up in algebraic geometry, or really they come from topological string theory. And there's two, I mean, there are many types, but there's two types appearing here. One is these genus 0 Gromov-Witten invariants, which somehow count numbers of curves mapping to your variety. So there's some base variety x, probably a Calabi-Yau threefold, and there are some numbers here. And it's an old story from the 90s, particularly the name Dubrovin would be associated with this, that using those invariants you can define some interesting differential geometric structure called a Frobenius structure. So this is some newer story, and it's absolutely not complete. But there seems to be some suggestion that this different class of invariants, these Donaldson-Thomas invariants, can also be used to define a geometric structure, and this is what I was calling a Joyce structure. And now, you might think, okay, well, that's just, why put these two things together? Probably these stories are completely different. And in many ways, they are completely different, but there is one very strong analogy between them, which is that in both cases, the geometry is basically about some isomonodromic family of connections. And I'm going to explain that, okay? But for some of you already know this. But the story is the difference between the two stories is that there is a different gauge group. So somehow here, all the connections are linear connections. There's something about GLNC, whereas here, what you're considering is this omega is a symplectic form, so n has to be even here. And you're thinking about symplectic automorphisms of space C star to the n. And, this is kind of a formal analogy in many ways, but that's what I'm going to explain here. And actually, I think it goes back a long way, this idea that Plavansky's equations are about isomonodromy. I think people used to write this as area-preserving diffeomorphisms of C2 or something like that. They were considering the two-dimensional case. Anyway, I'm going to explain that. And it was Ian Strawn that explained to me that this equation, so I kind of thought about the isomonodromy condition for connections with this gauge group, and I came up with this equation, which is not an amazing thing to do. And Ian explained to me that this was Blavatsky's heavenly equations, and therefore there's links to hyperkähler geometry and stuff. And I should say this question mark, so there really is no general theory yet. So, given the DT invariance, I can't define a geometric structure, but I can in some interesting examples, and you get some nice examples of hyperkähler structures, and it would be really great if we could do it in more generality, but there is some kind of serious analysis to be done there, which maybe will be clear by the end of the talk what needs to be done. Okay. So I'm going to tell you about Stokes data and isomonodromic deformations. So this is going to be the kind of crucial idea in the talk. And so we're going to start with this slide. Okay, so skip the first line to start with. What I'm considering is a matrix differential equation, or if you want, you can think about it as a flat connection on a trivial bundle over P1. But it's for maps from C star into GLN. Okay? So think it's just a matrix differential equation. So U and V are some matrices, constant matrices, and I'm trying to solve this differential equation, and my parameter is epsilon. That's my parameter on C star. It's not small or anything like that, right? Epsilon is allowed to be a parameter. Okay, so I'm considering this differential equation. And there is some constraint on what matrices I choose here. Basically, U should be diagonal, and V should have zeros on the diagonal. Okay, now, you shouldn't worry too much. So first of all, why should I consider such a differential equation, right? So the first thing to say is that we're used to considering differential equations with regular singularities, so with just kind of simple poles at points. That's typically what happens. You have a matrix equation like this. It has a bunch of poles, simple poles, and then you kind of compute the monodromy of the equation around these poles. That's a kind of standard story. This is not that story because there is a pole of order 2 here. So this is what they call an irregular singularity. And there's some new phenomenon happens there. You're not allowed to just consider monodromy. You should consider things called Stokes matrices, which I'm going to define in a second. So this is an equation with a pole of order 2, and it's basically the simplest equation with a pole of order 2. So all the rest of the stuff is just kind of genericity, really. I'm asking that U has distinct eigenvalues, and then I can diagonalize it by some gauge transformation. And then V, I'm assuming, has zeros on the diagonal. That's just to make things a little more simple. Okay, but later we're going to want to change the gauge group. So let's just think for a moment in a kind of Lie theoretic way. So this is the relevant group here. The relevant Lie algebra here is GLN, just n by n matrices. And I can split it into the diagonal guys, the Cartan, and the off-diagonal guys here. And we have this root decomposition. Okay, so hopefully this is kind of familiar to everyone. Any questions? Okay, so what do we do with this equation? So there's a basic fact about this equation, which is that there are canonical solutions in half planes. So to be a bit more precise, first I have to define a bunch of rays, and these rays are spanned by the differences of the eigenvalues of the connection, the differences of the eigenvalues of that kind of leading term, U. Okay. Now, if you're a fancier person, you can think of that as the pairing of U with a root, because kind of the roots of GLN are kind of EI minus EJ, and they naturally pair with elements of the Cartan, so you can think of this as a root. So there are a bunch of rays indexed by the roots of the Lie algebra, and then as long as you take here's the rest of the picture. As long as you take some ray which is not one of those, then there is a unique solution on the half plane centered on that ray. So the idea is that this ray R is the center of this, it shows the direction of this green hyperplane, green half plane, and there should be a unique solution to this equation in that half plane, which has certain asymptotics as you go into the origin. Okay, so it's an interesting thing. There are some kind of canonical solutions in half planes. I don't know whether this is the correct reference. I mean, it's certainly in here. Whether there was earlier, Okay, so that's very important, and let me just draw that picture because we're no doubt going to come back to it. this in some sense is the most important picture of the talk. So you have, you have some parameter epsilon in C basically, and you have a bunch of rays in this plane. This eventually is going to be the base of the Twistor family, Twistor space, but in a long time. But yeah, those rays are important. Okay, and then given that, we can easily define Stokes factors by just comparing these canonical solutions. Okay, so if I take some ray, like one of my red rays there, remember, as long as I choose something that's not a red ray, not one of these Stokes rays, then I can find a fundamental solution. So I can just perturb this a little bit, R plus and R minus. Here's my ray L. And then I can compare those two solutions, and that, because they're solutions to the same differential equation, they differ by a constant matrix, which is this guy. And because of that asymptotic property, you see, if I times this by e to the u over epsilon, whatever it was, and this one by e to the u over epsilon, then both of these will go to 1. So that tells me that if I conjugate this by e to the u over epsilon, it has a limit as epsilon goes to 0, which tells me that it can only have entries in certain places in the matrix. And so the clever way of saying that is certainly this is an element of the group because it compares two solutions, but it's in a particular part of the group, namely the bit you get by exponentiating the root spaces corresponding to roots lying on that ray. So I should explain this as well, actually. So I know it feels like I'm laboring this, but we're about to change into a different setting where this all becomes a little less obvious. So remember, these roots, you should think about them as like u1 minus u2. What would be another good one to do? u2 minus u3. And this would then be u1 minus u3. Right, so I'm doing the case of n equals 3. So there are just 3 eigenvalues, and the rays are based on the differences between those eigenvalues. But this is kind of a generic story. You could have a picture. You could have a picture where these rays line up, right? So u1 can't be equal to u2. One of the conditions was that the eigenvalues were different, but they could at least line up, right? So you could have a situation like this, and then this Lie algebra, this bit of the Lie algebra is bigger because it contains all the roots at that point. So we're saying in this special situation, this would be something like any upper triangular matrix you associate to this. But in this kind of generic situation, the thing you're going to associate to that is going to be something like 1, 1, 1, something here, 0, 0, 0, 0, 0. Right? It's an exponential of something corresponding to that position, and likewise here. So it's very important because this is going to be the kind of whole story of this talk. A bunch of rays in the complex numbers labeled by elements of a group. Okay. And so how do we define this thing? Oh, this is the picture. Yeah. How do I go back? So that's one perturbation of this Stokes ray L. There's a solution in that. The other perturbation R minus, there's a solution in that, and then I can just compare them on the intersection. Okay, so that's how we get some matrices out of this. So I hope this is comprehensible. And now this comes the tricky bit. Now we want to think about deforming. So maybe I should write my equation just because it's gone. dy over d epsilon. Okay, so that's my equation. I now want to think about deforming these matrices and seeing what happens. And so, in particular, as I vary my leading term u, it turns out that you can uniquely deform v so that these Stokes factors remain constant. So that's called a kind of iso-Stokes or isomonozomic deformation. So there's two things I have to say about this. Maybe I've put them in the wrong order. Let's just see them all. The first one is that if you want to vary v so that the Stokes factors remain constant, that involves a differential equation on v, system of PDEs basically, and this is it. So if I decompose v into my root spaces, so in other words, I'm just taking my matrix and thinking about the entries of that matrix. That's what these v gammas are. They're just the entries of the matrix. then there's something about d of that equals some bracket of these, so it's kind of quadratic in the other entries of the matrix. And this is a function on my space, because as u is varying, u of beta, something like u1 minus u2, something like this. So this is some system of PDEs which tells you how v varies with u so that the Stokes data is constant. Okay. And to spoil the punchline, this is going to turn into that Plebanski equation. Right, so. And then, but there's another thing I need to say here, which is just that it's a little bit lazy to say that the Stokes factors stay constant.
Sorry, I have like a kindergarten question.
Sure, I like those.
It doesn't look symmetric under alpha and beta.
Why is that? You mean this, right?
The right-hand side of the equation.
And why is that a problem? Oh, you're thinking...
I thought it didn't matter the view as a function of beta or as a function of alpha.
No, this is kind of important. So I haven't thought about this. So certainly I wouldn't want to write d log u gamma here, because this would be skew symmetric. So when I summed over all decompositions, I would get 0 on the right-hand side. Okay, so I do need to break the symmetry in this equation. And I claim this is the right thing to do. I mean, I could also put u of gamma there. And then
put u of alpha.
Sorry, I could also put u of alpha there. And that would just change the sign, yeah.
And this is some Panlevet equation, or some generalized Panlevet equation.
Yeah, I mean, I guess it has the Panlevet property, probably. So, yeah, I mean...
It's called Schlesinger, maybe. Yeah.
Well, so it's what people call the irregular Schlesinger equation. So the Schlesinger equation would be about a differential equation with regular singularities. And exactly the same, yeah, I mean, absolutely is the same neck of the woods. If you're deforming the residues of that connection, there will be some equations that told you the monodromy was constant, and those will be the Schlesinger equations, right? Yeah.
Right. So I think Brogan had some sort of Laplace transform from that representation as well, which was actually probably Schlesinger.
Absolutely, yeah. So that's absolutely correct. So one way, I gave you that theorem about existence of solutions in half planes. How do you prove that? You basically do a Fourier Laplace transform. And the Laplace transformed connection has got regular singularities.
Right.
So yeah, indeed, these connections can be related to connections with regular singularities via Laplace transform. It's an interesting remark. More of it. Okay, so the other thing I was saying, so I was just saying that it's a bit lazy saying the Stokes factors are constant. What you really want, because we're allowing u to vary, these rays could collide. Okay. So I've got an example which should hopefully make this clear. So let's consider the following situation. I couldn't be bothered to tech this last night. So we're considering a situation where these u's are moving around in such a way that this ray and this ray cross each other, right? And in the middle, the rays are just lined up. And I'm claiming that, associated to this ray, there is some matrix, and it would better be of this form. And likewise, associated to this ray, it better be, that's definitely a typo. Sorry, where's the chalk? Like that would better be of that form. And the point is that when we cross, we have to then have matrices of this form associated to these various rays. And the claim is that these matrices uniquely determine these matrices, right? So if you multiply all these matrices together, so you get this. Now, if you want to express it as a product of matrices of this form, so you're only allowed something there, you're only allowed something there, you're only allowed something there, then there's only a unique way of doing it. So you see, these entries determine these entries. And this is like a wall crossing formula. This is, to again spoil the punchline, this is going to turn into the Schlesinger equation. This is going to turn into the heavenly this equation. And this condition on the way the Stokes factors change is going to be the wall crossing formula in Donaldson-Thomas theory. So I'll explain a bit more about that. But so the interesting thing about these things is that as you vary the UIs, the entries of this matrix have to remain constant. And that's the condition. They sort of remain constant up to a point, up to a wall. The wall is where these two things line up. And then there will be a sudden change, and the numbers appearing in this matrix, like in particular in this matrix, just suddenly changes. Okay. And that's the name of the game, basically. Okay, so it turns out that in this story in enumerative invariants, we're being given the equivalent of this data. We're being given the Stokes data, and it changes in a particularly interesting way, which people took a long time to understand how it changes, and it turns out it changes exactly like this, except that there's a different group involved. But anyway, so people eventually understood that, and then if you know this story about Stokes data, that kind of forces you to realize that you should write down this equation for the corresponding Lie algebra, and then you realize that that's the Blavatsky equation. So that's somehow the story. Any more questions? Yeah, and so for those who know about Frobenius structures, a solution to this equation is almost the same thing as a semi-simple Frobenius manifold. So if you have a semi-simple Frobenius manifold, you do indeed get an isomonodromic family of connections of this type. You do indeed get a solution to this equation. Going the other way, you need a bit of extra data. You need the identity of the Frobenius manifold. So I mean, Ian's the expert here, but roughly, from a distance, you could say that this is kind of the same data as a semi-simple Frobenius manifold. And this is kind of a service slide for Sergei's talk later. So maybe it's worth just saying that the game here is that we fix U. I mean, we were varying U there, but let's think about for a minute fixing U, and then we have V, which is this off-diagonal thing, and we also have the Stokes data. And we should consider that for all the Stokes rays at once. And actually, if you look at all the data there, that is also an element of G odd, and there is a map like this. So, given V, you can compute the Stokes data, and this map is almost an isomorphism. So if you make things fancy enough, there is something called the irregular Riemann-Hilbert correspondence, which says that connections up to gauge equivalence are equivalent to their Stokes data. So you have to do things like allowing a more general bundle and things like that to get a complete equivalence. But this map is nearly an isomorphism, so you can ask the question, how would I go from here to here? Given that I've told you that in DT theory we're going to be given the Stokes data, it's an interesting question, how would we actually get this? And so just very quickly, what you have to do is you have to try and construct these half-plane solutions. Because once you've got the solutions, of course, you can just differentiate them and get V. Okay, so how do you get those solutions? Well, they're kind of characterized by their properties. They have asymptotics at 0 and infinity, and they differ by certain specific jumps. So you end up with something called the Riemann-Hilbert problem, which basically says that looking in each half-plane, you should find some function with this asymptotics, which is what we insisted upon. It should have some kind of moderate growth at infinity, because that equation has a regular singularity at infinity, this one. And they should differ. If you take two different rays, they should differ by the corresponding product of Stokes matrices. Okay, so yeah. So even in this linear case, this is kind of a pretty non-trivial problem. But it is basically what goes into the proof of this irregular Riemann-Hilbert correspondence. Some argument like, showing existence of solutions to these things. Okay. So now I need to tell you what gauge. So that was kind of the baby case. It's already a kind of interesting piece of mathematics. And now I want to tell you what is going to replace this algebra of matrices, this GLN, and it's going to be a Lie algebra of symplectic vector fields. Okay, so yeah. So I'm going to start with some lattice, just z to the n, with some skew symmetric form, and for simplicity, I'm going to take it to be non-degenerate. Okay, so out of the lattice, I just build a torus, so C star to the n, but it's an algebraic torus whose characters are indexed by the elements of this lattice. So I just look at maps from gamma into C star, and then this form will give me a Poisson bracket on this torus, which, because I'm saying it's non-degenerate, is actually going to come from a symplectic form. So these are characters. So, oh, well, I just said this here, right? So for every element of my lattice, I have a character of my torus, and I'm telling you what the Prassam bracket is on those characters. I mean, this is an invariant symplectic form, right? So this torus is a group, and this symplectic form is invariant under sort of translations in that group. And what I want to consider, just heuristically for now, I want to think about the Lie algebra of algebraic vector fields on T. So of course, if I ever do any proper analysis, I'm not going to be allowed to consider algebraic vector fields, but let's just think about algebraic ones for now, whose flows preserve omega, so symplectic vector fields. So we can actually sort of put our hands on those. So there are kind of two types of vector fields. There's Hamiltonian vector fields, and there's these translation invariant vector fields, just kind of translations around the torus. And you should think about the translation invariant guys as being the Cartan, so H. And so what's a translation invariant vector field? I can just identify it with its value at the identity of the torus, and that is just you know, an element of the tangent space at the identity, which is just the dual, just this maps from gamma to C. And what are Hamiltonian vector fields? Well, they're just kind of given by functions on the torus, non-constant functions. So that's these things. So non-zero elements of the lattice, combinations of characters, basically. Okay. And so the analog of the root system is just the kind of Fourier decomposition of a function. So it's given by the characters, the non-zero characters. Okay. So then what we do is we just do everything we did before, but with this Lie algebra. That's the idea. And so, right, so maybe I just go through. Yeah. So, indeed, I'm going to write down the same equation. And it's convenient here to introduce some different letters because they're standard in DT theory. And it's kind of handy anyway, because U is a translation invariant vector field. I'm confusing it with its value at the identity, which I'm going to call Z. And similarly, V is a Hamiltonian vector field, but I'm going to denote it by the corresponding function F, which has some decomposition like this. Okay. So now remember the rule about how do we find the Stokes rays. The Stokes rays are the pairings of the roots with the kind of leading term here. So really they're just the Z of gammas. So Z is a map from the lattice to C, and I just take their value on these gammas. So now we're going to get a countable number of rays, because the gammas are living in some lattice. Before we really had just some finite number of rays, so that's one difference. And then what do the Stokes factors look like? So it's the same formula. If you think, right, that formula always involved an exponential. So in the case of matrices, that was just taking the exponential of matrices. But now we've got to think about going from the Lie algebra to the Lie group. What does it mean? It means we take the time one flow of a vector field. And that might not be well defined. But anyway, so here's a function on the torus. Poisson bracket with that defines me a vector field, and then I take the exponential, i.e. time one flow. And that is supposed to be living in the group, which is going to be the symplectic automorphisms of the torus. And at this point, this is becoming a bit iffy, right? Because there are various, well, in particular, this time one flow might not exist. There is not a well-defined exponential map from the Lie algebra to the Lie group. This is an infinite dimensional group, and so on. Okay, so at this point, it's becoming a bit heuristic. Also, I mean, the fundamental thing, how do you define Stokes data? You need the existence of these canonical half-plane solutions. That was a theorem. It doesn't apply to this Lie algebra, so we don't know that either. So, so does this converge? I mean, does this time one flow converge? Okay, so at this point, it's becoming a little bit heuristic, but you can still do two things. You can still just formally figure out what does that isomonodromy differential equation look like in this case. And you can also look and see what does this rule look like in this case. So those two things are perfectly well defined, and it's really just the map between them that is now becoming extremely hairy. So, this differential equation makes perfect sense if you write some Lie algebra on the torus, some vector field on the torus. That makes, you can write down this differential equation. These numbers, after all, in here there are just some numbers depending on the points of the lattice, and the transformation rule of those numbers makes perfect sense as well. What's very tricky is how do you get from the numbers to here or from here to the numbers, and basically we don't know. So now let's suppose we have some family of equations parameterized by some complex manifold. So in other words, what I'm saying is that the data Z, remember, we're now in a situation where this is somehow corresponding to this was a translation invariant vector field, that it corresponds to some element here, and this is corresponding to some function on my torus. So this data is now varying over my manifold, and so I can build this function. So this is a function on the torus cross my manifold. So Z is varying on the manifold. This is varying. This is a function on the torus. These are numbers, but they could vary on n. And so I can form this function, and then if I express everything in a basis, so I should take a basis of the lattice and so on, I get this equation that I wrote before. So I claim that's kind of an easy exercise, that if you just take those isomonodromy equations that I wrote before, they kind of apply, that's the kind of general form that applies to any Lie algebra. If you kind of express them for this Lie algebra, you get these equations. And I think in some sense this has been known for like 40 years or something, that the Plebanski equations are isomonodromy for some different Lie algebra, which is something to do with area-preserving diffeomorphisms. I think this is, I guess, Mason and Newman say something about this.
I mean, it's in Roger's original paper.
Yeah.
Doing, going back to the 1760s, metamorphisms to blue Twistors.
Yeah, well, of course, it's true that, I mean, it's clear that symplectic geometry has a lot, I mean, once you understand Twistors, but I don't know about this isomonodromy equation, but certainly this has appeared. But I think what hasn't really been thought about is what is the Stokes data of these connections, which are, being isomonodromically deformed, and that's where this link comes in. And so this is just, you wanted me to say something about DT invariance probably, and you're going to be very disappointed. This is the slide where I tell you what's, this is the kind of popular math slide. So I just tell you some words. You don't have to think. So there's something called a CY3 triangulated category. So the best example of that would be the derived category of coherent sheaves on a smooth projective Calabi-Yau threefold. Right, so this is the B model in topological string theory. Or there's the Fukaya category is another example of these. But there are tons of other examples, and as we were discussing with Lionel yesterday, the reason to do a more general thing is not to be more clever, but to be less clever. So the derived category of coherent sheaves on a Calabi-Yau threefold is extremely complicated, and it's very hard to do things with it. There are tons of examples of these just coming from algebra, just little quivers and things, really algebraic little things that you can really get your hands on. So that's why we want this greater generality. Although I should say that for what's on this slide, we sort of know how this works for the quintic threefold, for the derived category of coherent sheaves on the quintic threefold. In that, yeah, so I'm going to talk about stability conditions and DT invariance, and due to some incredibly hard results of Chunyi Li, for example, we do know that we can do this for the Calabi-Yau, for the quintic threefold. That's kind of sort of amazing. But I spend my time thinking about much simpler examples. And then there is this thing, the space of stability conditions. So this is going to be our base M. This is going to be where this kind of Plebanski equation is living. Yeah. And so I'm not going to tell you very much about this, apart from that a point of this space parameterizes two pieces of data, one of which is some subcategory of the category which is considered to be, these are the objects which are considered to be semi-stable. So there's something like BPS branes in physics. That's what, and indeed the definition of this came from physics, work of Mike Douglas. And then there is some data, essential charge. And of course, this is exactly what we wanted, right? Oh yeah, and I forgot to say this in my excitement. So you have to sort of just fix a map from the Grothendieck group to gamma. So what it means is that every object in your category has a class in gamma, and if you have a triangle, then those classes are additive. And then the important result about, I mean, you write down these things and you write a system of axioms they satisfy, and then the slightly amazing thing is that you can get geometry because this map is a local homeomorphism, so you can use the, this is just C to the n, so this is a complex manifold. You can use that to induce the structure of a complex manifold on here. So, and this was Mike Douglas's intuition that somehow this data is such that if you deform Z, there is a unique way of changing the subcategory of semi-stables so that all the axioms still make sense, that they're still satisfied. So in our case, this is kind of perfect. And then there's a massive story here, hundreds of pages of very difficult work tell you that you can you can define moduli spaces and try to take their virtual Euler characteristics, and these will give you some numbers. And the important thing about these numbers is that as you vary the stability condition, they change in some very interesting way, and the claim is it's exactly this way we had before. So they're locally constant on this space of stability conditions. There's a bunch of walls, and as you cross a wall, you have to write down the equality of two products. On one side of the wall, you have a product of elements of a group, and on the other side, you have a product of elements. That group is the group of automorphisms of some symplectic torus. And yeah, that is the condition. And just as before, if you know all, the amazing thing about this is if you know all the DT invariants at one stability condition, in principle, you know them for all other stability conditions in the same connected component because you can just keep applying this wall crossing formula. So it's a beautiful thing that somehow stability conditions from very far away from each other that don't look like they have much to do with each other, you can really, the invariance of one completely determine the invariance of the other, but not in a boring way, in this kind of quite non-trivial sort of way using identities like this. Okay. Right, so that's the end of the kind of lesson in isomonodromy and so on. So of course we would like to turn this into rigorous results. We would like to be able to, given these DT invariants, define a solution to that equation, and that seems to be kind of a difficult thing, but maybe it's within reach. But probably we need to go via some of the geometry associated with this equation. In particular, maybe the Twistor space. I think the best hope of solving this problem is using the DT invariants to define a Twistor space, basically. And then, okay, well, but maybe we'll come back to that. So let me just say a little bit about the geometry of this equation. So this is something that probably many of you know, but I'm going to say it in a fancy way to confuse you. So what I want to think about, we can forget about the rays. I realize this is a painful way of writing it for some people, but maybe we can get rid of this. So I want to think about a complex manifold, and I want to think about its tangent bundle. Because I want to think about connections on the tangent bundle, but they're not going to be linear connections, so I need to kind of draw it geometrically. So here's X. And just
Holomorphic tangent bundle? Holomorphic connections or what?
yes, absolutely, yes. Yeah. So here's N, and here's X, and here's the projection, and so here's a fiber, which is just the tangent space at that point, so it's just some vector space, of course. And the first, so here I've just applied, and maybe I write this down here, so I can just, what do I call it there? Oh, yeah, okay. D pi, right? So I'm really doing something trivial here, right? There's a map between the tangent, there's a projection from the tangent space. I'm thinking of this as a complex manifold. It has a projection to M. I can take the derivative of that projection. I get a map from the tangent space of X to the tangent space of M, except really I should pull it back so that all these bundles are living on the same space. And the kernel is just the vertical tangent directions. Okay, so the first thing to say is that what's a nonlinear connection is just a splitting of this map. So, I've written pi star, that's terrible, sorry. So it satisfies d pi composed with H is the identity. Right, so it's just a way maybe I do it in blue, is just a way of lifting this tangent vector to some tangent vector upstairs. And because the connection is non-linear, there is no relation between the lifts here, 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 and here. Right? So we're not using the kind of linear structure on this space. So that's the lift of that's a non-linear connection. And the other thing that we have here is we have some canonical isomorphism here, which is confusingly trivial, which is just saying that a vertical tangent direction is a tangent to the fiber. But the fiber is a vector space, so a tangent to that vector space is the same as an element of the vector space, which is the same as an element down here. So if you think of a tangent direction to M, it sort of canonically gives you a vertical tangent direction at this point as well. So there are also these kind of vertical lifts at each point. So I think I've put this I, and then I want to consider this composite. V is I. Okay, so that's the picture that goes with this. And then, sorry for this horrendous terminology. You just have to think I'm an idiot and forget about it. Okay, there are reasons for why all this stuff got labeled by strange names. But anyway, so this is some piece of data. So I want a complex manifold, I want a symplectic form on my complex manifold, and I want a nonlinear connection, as I've just discussed. And then the point should be that, you see, I can combine these connections. I can combine this connection with the vertical map. So epsilon is some parameter, just in C star. You see, if I compose with this map V, so I guess the point to note is that d pi composed with V is 0. If you're a short exact sequence person, you realize that. But yeah, just because it's a vertical tangent direction, right? So when you project it, it goes to 0. So, so these are all suitable nonlinear connections, and then I want them all to be flat and symplectic. So maybe I should say what flat and symplectic means. Symplectic, you see, because I have a symplectic form here, each of these vector spaces has a linear symplectic structure on it, and I just ask that the parallel transport of this connection kind of preserves those symplectic forms. And flat means flat, so I guess it preserves, this lifting, this H, preserves Lie bracket, is one way of saying it. Or another way of saying it is that there's some local coordinates here such that these tangent directions are just got by setting, these blue arrows are just got by setting those coordinates to be constant. Something like this.
The image lift is
The image, excellent, thank you, yeah. The image of H is an integrable subbundle of the tangent bundle of X. And this immediately gives you a kind of hyperkähler structure, because the tangent bundle of X now splits into two pieces. They're both kind of the same. They're both the tangent vectors from downstairs, so the image of the horizontal guys and the vertical guys. And then I can just write down some kind of standard hyperkähler, you know, some standard action of the quaternions in this decomposition. I will get, well, it looks like I get a hyperkähler structure, but the crucial thing is that this condition that these are flat and symplectic is exactly what you need for this to be integrable, for the, you know, I, J, and K to be covariantly constant, and so on. So this is just some fancy way of re-expressing something that everybody knows, I think. But from the point of view of Frobenius, it's kind of, from the analogy with Frobenius manifolds, it's quite nice, because a Frobenius manifold is essentially, the first thing you say about it is it's a pencil, i.e. a one-parameter family of flat connections on the tangent bundle. That's usually what people say. So here we've got the same sort of thing going on. We've got a one-parameter family of connections on the tangent bundle, but they're no longer linear. They're still flat, but they're no longer linear connections like they were in the Frobenius case, but they are symplectic. So you can sort of see that we've replaced the group GLN, which is about linear connections, with symplectic automorphisms, which is about, you know, symplectic connections, symplectic nonlinear. Okay, and if I just write this in coordinates very quickly, so if I take coordinates down here on my manifold M, and I'm going to take them to be kind of Darboux coordinates, so remember I have a symplectic form down there, so I have Poisson bracket, and I ask that that's constant. On the tangent bundle of M, I then get coordinates by, you know, I just write a tangent vector as a combination of the kind of basic tangent vectors. So the coordinates upstairs are now z's and thetas. And if you do that, you see that this vertical lift, which was always a kind of trivial thing, is really just this. And these horizontal lifts, you can write them in a kind of, because they're this is a symplectic connection, you can write it as a kind of Hamiltonian way, which is what I'm doing here. And then if you impose flatness of this combination, h plus 1 over epsilon v, then you get these equations. So that's just sort of telling you that this abstract nonsense, this kind of geometric story I was telling you here, gives rise to those connections. Gives rise to those equations. Okay. And then I feel, yeah. So I should emphasize that when I first defined the term Joyce structure, it was because I'd written this equation down and I had no idea what it meant. And Joyce had actually done some preliminary work on trying to understand geometric structures defined by DT invariants, and he basically thought about very similar things. So I thought it was appropriate, let's label it Joyce structure. And then it's a bit tricky now because this in many ways is saying things that people already know. However, it is useful to have a word for a solution to these equations which has certain extra properties, which is what naturally comes out of this story. So I'm just going to explain those properties. So, so they're all just extra symmetries of this solution. So the first one is that here I was talking about the tangent bundle, but actually it's not really the tangent bundle we're interested in. What we're really interested in is a bundle whose fibers is C star to the n. So I tend to draw it like this. So it's just gotten by quotienting the tangent bundle by some lattice living inside it. Okay, and it just means that this function is actually periodic in the theta coordinates, and so the correct coordinates are e to the 2 pi I theta, not theta. So that sort of explains why we had this algebraic torus knocking around earlier, right? So it was really a C star to the n that was relevant, not C to the n. So that's the first thing. The second thing is that this killing vector field. So there should be some C star action, such that the vector field scales the data in this way. And that again corresponds to some homogeneity property.
In terms of the rank of the torus, is it real rank half the real fiber dimension? The quotient, is it a compact torus or is it
it's an
product of C stars?
It's a product of C stars, yeah. Thanks. Yeah. So this actually comes about again. You can look at it. You can see it from that isomonodromy equations. If you look at the equation that I wrote, this guy. I mean, this whole equation is invariant under rescaling u and epsilon. So everything, there is some kind of C star action here which just doesn't change anything. So if you trace that through, you see that the function w you built has some kind of homogeneity. And then this is so of course the tangent bundle has -1 acting on it, so it gives you an automorphism of this torus, an involution of the torus, and you ask for this. And this symmetry comes from the fact that the dt invariant of gamma is equal to the dt invariant of minus gamma. So there is some symmetry there which translates into this. Okay, but that's some extra. So a Joyce structure is one of those things I had before, plus these conditions. And those are the things we're interested in. Okay, so I must have been going too fast because I have 10 minutes, so that's nice. So I want to just briefly discuss some examples of these things. And so
The talks are nominally 15 minutes long, right? So you're doing. Don't worry about having not gone fast enough.
Oh, really? So I'm supposed to stop after 50 minutes, am I? Is that the?
Not a lot of questions, I believe. The organizers can tell you better than I can.
Just carry on and
Yeah, okay, I think I have 3 more slides, so I think some compromise between those two things should be possible. Okay, so I just want to describe a class of examples. They're indexed by a genus and a collection of whole orders. And the base, so, these joy structures always live on some complex manifold, and the base of this complex manifold, in this case, the complex manifold is a space of quadratic differentials. So it's a space parameterizing a compact Riemann surface of genus G. So I really do vary the curve, that's important. And I take a quadratic differential, so a section of omega squared. It should have poles of order mi's. And it should have simple zeros and a little technical thing. So if you have a quadratic differential with an even order pole, there is something called the residue. These things are typically mass parameters in physics, and I'm actually setting those to be 0. Okay, because then this space is symplectic. Otherwise, it's Poisson. That's not so nice. And so we have a theorem that, so in the case, so I'm on the archive, this exists on the archive. It's a construction of a joy structure on this space of quadratic differential in the case of no poles. And the extension to the case of poles is I'm working on it with my PhD student, Menelaos Sikidis. And actually the case with poles is more interesting in many ways. In particular, there are 10 cases when you take genus 0 and this moduli space has dimension 2, and these correspond to the Pain-Levé equations. And the joy structure very much knows about those Pain-Levé equations. I mean, what's a better way of saying it? So, well, maybe when I explain the proof, actually, you'll see it. Okay. So there's only one page of proof. It's not really proof, it's a summary of the construction. So I just go through it quickly. So if you have a quadratic differential on a curve, it defines some double cover, just given by y squared equals q. And the reason I care about that is that the tangent space to the moduli space of quadratic differentials at some point is the first cohomology group of that double cover, anti-invariant. So there's a covering involution, and I ask for the anti-invariant part of that cohomology group. And so remember, so this obviously has an integral structure living in it. So remember, this joy structure, you needed some kind of lattice living inside the tangent bundle. And indeed, inside the tangent space, which is this, of course, there's an integral cohomology, so that's good. And I'm interested in the quotient. And what I get is essentially C star cohomology. There's a subtle thing about spin structures, don't worry about that. And so the point is that you can represent elements of this as the holonomy of line bundles with connection on the double cover. So this is the key thing. So somehow, so we have this space. This now is my space of quadratic differentials. And this, remember, I've replaced this c to the n by a c star to the n. I've quotiented. And this guy is really h1 of sigma c star. Okay, so, and I need to make a connection on this. So I need to tell you, if you move the quadratic differential a bit, how am I going to move an element in this cohomology? It's kind of scary because the spectral curve is changing and everything. And I need to give you a whole family of ways of doing that, epsilon, depending on epsilon. So this is what I do. I think about this as the holonomy of some line bundle with connection. Okay, so that's fair enough. I can do that. And then I apply the spectral correspondence. So here's sigma and here's C, and there's a very old story about how a line bundle on the spectral curve gives you a Higgs bundle downstairs. Okay, so this is a fundamental part of Nigel's work. But the tricky new thing here is that I had a line bundle with connection. And the slightly surprising thing is that you can extend this correspondence so you actually get a connection down here as well. This is not one-to-one. There's some kind of problem here. There's sort of birational issues. But generically, you can indeed turn this into a Higgs bundle with connection. And then I know how to move these things, because as I vary the quadratic differential, I just insist that the monodromy of this connection is constant. So anyway, it's a construction, and the great thing is that in examples you can really compute these things. So isomonodromy connections, they're kind of computable things. It's an algebraic. The isomonodromy connection on the moduli space of vector bundles with connection is an algebraic connection, and in examples like those Pan-Lavey. So Pan-Lavey equations really describe these isomonodromy flows. So that's why you're getting a link with that. Okay. Right, so that was that. So last slide, some further directions. So the twistor space finally made an appearance. Apologies for that. So of course you can take the twistor space of a joist structure, and because it's got a hyperkähler structure, it has a twistor space. But in this case, you can rewrite it. It's just the space of leaves of those connections. And I mean, Nigel was talking about similar things yesterday. So in this case, I said there was a C star action on X, and that was part of the joist structure definition. It rescaled it fixed one of the complex structures and rescaled the others appropriately. So it turns out that this is a case where there's a C star action on Z, and this map is kind of equivariant, right? So the C star action on Z maps down to the C star action on P1. And so in that situation, you've basically got 3 twistor fibers, right? Because the C star is just moving all the twistor fibers into each other, apart from Z0 and Z infinity, and all the others get mapped to Z1. And Z0, you can kind of see, has to be M, right? Because, well, yeah, maybe that's obvious to you guys. Right, so Z0 is the thing you started with, and you get these 2 other things. And in these class S examples that I was just talking about with poles, there's something very interesting happens, because this space of quadratic, so these examples are related to this whole story about DT invariance. Maybe I should have said that. So these spaces of quadratic differentials, so work of mine and Ivan's, identifies those spaces as spaces of stability conditions on some suitable CUI3 category. So that the last 2 slides were an example of what I was talking about in the previous time. Right, but this is kind of now getting more for experts. Those categories are described by quivers. And the really interesting thing is that Z0, by my work of, by the work of me and Ivan, Z0, which is M, is this kind of space of stability conditions, space of quadratic differentials. Z1 is also defined by that quiver. Z1 is basically the cluster variety of that quiver, because you can see how by the way I constructed those isomonodromy connections, the space of leaves is just the set of monodromies. Right? I said I get the flows by fixing the monodromy or something. So the space of leaves is something to do with the set of monodromies. And in these kind of wild character varieties, there's work of Fock and Goncharov which explains that those wild character varieties are cluster varieties. And it's actually for the same quiver that appears in mine and Ivan's work. So I think this is an extremely kind of suggestive thing. I think I will leave it at this point. But so the big question is, given the DT invariance, can we construct the joist structure, right? And so I explained this Riemann-Hilbert problem business, okay, in the GLN case. So you could imitate that, and you can play with that, and definitely you can do some stuff. But after a while, you realize that what that amounts to doing is actually constructing the twistor lines. So what's happening is that the twistor fiber at Z, if you have a twistor line, you can just kind of push it into Z1. And so, using the C star action. So you just get a map into Z1, and you're expressing that in some particular coordinate system. And these jumps across the rays correspond to changing the coordinate system on Z1. But in any case, solving the Riemann-Hilbert problem really is expressing the twistor line. And maybe, one lesson I've learned from twistor people is that, the magic of the thing is that you can build the twistor space and then just sweep under the rug the twistor lines, know that they exist abstractly, and if you really needed to find them, you could. But it's easier just to construct the twistor space and use abstract results to show the existence of the twistor lines. So maybe we should take a message out of that and not try and solve this Riemann-Hilbert problem too much, but just construct this twistor space. And so I'm doing some work with Helga Ruddat where we basically do this in the case of ADE quivers. So we take the cluster variety and degenerate it to the stability space, sort of actually build the degeneration. And it's definitely not finished yet, but so I think that's somehow the direction we're going in. But I'll stop there. Thank you.
Questions?
In practice, this generic Z0, is that an affine variety or something more complicated?
So it's a Z0, yeah. What tends to happen is that Z0 is a kind of universal cover of something like a hyperplane complement. That's the sort of things to think about. I mean, that's definitely not a theorem, but that's the flavor of what you get. So, yeah, so.
So you don't expect any compact subvarieties in that?
No, but the questions of partial compactification is an interesting one. I mean, another way of thinking about what this is so the space of stability conditions via mirror symmetry is quite like the space of complex structures on the mirror, right? So you should think, what does a moduli of complex structures look like? It's some space of more general varieties minus a discriminant locus usually, right? So there's a kind of a compact thing out there which is parameterizing, I don't know, K3 surfaces with some singularities. And then you have to take those guys out to get the genuine K3s. It's very similar in this. So that people are asking the question, can you put these things back and can you think about a more general space of stability conditions where you get more compactness, basically. So, yeah. Any more questions?
So the kind of picture one should have in mind is that M is a Stein manifold, but Z1 and Z infinity are conjugate to each other, and that they have a lot of compact cycles of them?
Right, so these are good questions. I mean, Z1 is these cluster varieties are affine, aren't they? I mean, the union of affine. Sorry, I'm not very good at thinking about affine. I mean, a cluster variety is a union of C star to the ends glued together by some birational maps. So that's also not a very compact thing. Again, there is some story about compactifications of those. So yeah, maybe I don't know enough about the compactifications to answer your...
No, I wasn't thinking about the compactifications, I was thinking of the actual fibers there.
Mm-hmm. So in DT theory, at least for toric Calabi of three singularities, that there's this notion of define invariants.
Right.
You have a candidate for a geometric picture that you can associate with this defined invariants.
No, and I know Ian is thinking about these things in Strom here. So yeah, so indeed, what Boris said. So the wall crossing formula in DT theory is about how some numbers change. I mean, it's a different group, but we can imagine it like this. So they're rational numbers. But there is a refinement of that, a canonical refinement, where these things become essentially kind of Laurent polynomials in Q, something like this. And that's a very natural thing in DT theory. So it means that the whole story, and this being the limit Q equals 1 somehow. So the whole story has some kind of refinement where you introduce an extra parameter, and it has a quantum flavor to it. So instead of the group of automorphisms of the symplectic torus, you would have the wall crossing formula takes place in a group of automorphisms of, well, it takes place in a quantum torus, so some non-commutative version of the torus, the linear functions on the torus. So yeah, so I don't know what the right way of thinking about the corresponding Plebanski equation and Moyle deformed and so on, but yeah, there is on the DT side there is some canonical quantization going on, and it would be nice to know in the geometric side what that's about. Yeah, sorry, I just repeated your question. I don't know the answer.
Is the fact that you could only get the connection on the Higgs pair generically why you get a meromorphic W, and is that why it's really birational automorphisms of a torus?
The first one, absolutely, yeah. So that, yeah, I didn't have time to mention that. So these examples that I'm trying to push, then in a way they're not genuine examples because W has some poles, but of course that's great, that's fine. And those poles are exactly related to this issue, that only generically you have, will the connection upstairs induce a connection downstairs. There's also some other source of issues, which is to do with this thing that they call the wobbly locus in Higgs bundle moduli space. So I would claim that those poles are actually super interesting. Definitely a feature, not a bug. The lack of birational transformations of the torus, I think, is. I think that's always going to be an issue, basically. I mean, like even the cluster structure on the Twistor fiber Z1 is only birational. I mean, those cluster coordinates are not defined on the whole wild character variety. So I think, yeah, I mean, you never. I mean, I told this story using a Lie algebra of algebraic vector fields, but of course that was just a trick. I mean, in the real world, you would have vector fields which were only defined on analytic open subsets and things like this. You know, there's stuff to be done.
So I have one perhaps final question. So to me, a Joyce structure sounds like the complexification of the construction of a semi-flat hyperkähler manifold from a special Kähler structure on N. I mean, you have an flat affine structure. I mean, it's just like a. You start with a. I mean, the special Kähler has a real flat affine structure. It has a real symplectic form.
Yes.
And you construct out of that, actually, it's cotangent bundle, a hyperkähler metric, and then you could take a quotient by the group gamma and get a torus, a real torus bundle, compact torus bundle. This is like looks like a complexification of that definition somehow.
Yeah, that seems a very reasonable thing to say. Yeah, I don't understand the. I mean, I think in this Boris, I'm sure will know better than me, but I think in this original Gauter-Moore-Knightsky story, which I should have mentioned, which is another story relating DT invariants to hyperkähler geometry, I think that thing gets called the semi-flat metric there, right? And that's some kind of limiting, you know, less interesting hyperkähler structure than the one they're trying to build.
Okay.
Now, my hyperkähler structure is also less interesting than the one they were trying to build. You know, it's this conformal limit. But the relationship between those two limits, I guess I don't understand.
Well, perhaps we better wind up and get some coffee. So let's thank you.